Hey everyone, we're going to talk about continuity now. We're going to break it up into two different videos. First, we're going to look at continuity and the types of discontinuity from a graphical point of view. The second video will discuss how to solve these algebraically. Let's get into it. We must first start by discussing this. It's something we already know. We've talked about it. Well, sort of. The only new piece is this right here. All right. If that wasn't there, all I would be asking you is, does the limit of some function from the left equal the limit of some function from the right? And if that was the only thing I was asking you, you should be able to look at this graph and tell me yes or no. Well, from the left side here, this is where x is approaching c from the left side. You can see every time we get closer and closer to c, we are approaching this y value, L, right? And quite honestly, if this is your x value c, whatever that L value is, well, technically f of c, right? Let's look at the other side. Let's do it in green. From the right side, well, this would be your function as x is approaching c from the right side. You're on your function and your x values are getting closer to c, and you can see as well you're approaching the same thing, L. Now, this side right here is approaching L, and this side over here is approaching L, so, well, the limit exists, and it's L, whatever that is, 5, 6, 7, you pick the number. Well, this one extra piece right here, for a function to be continuous at that same x value, in this case I called it c, the only extra thing that has to happen is that must also equal L. And then if that's true, then it's continuous at that point, whatever x equals c is. And what would happen is instead of a hole, you would see, here, let me change this to blue, just to make it look. And so if this was blue as well, what happens is, not only does the limit exist at x equals c, but it is also continuous at x equals c. As we just stated, if this holds true, well then your function is continuous at that specific x value, whatever x value you're talking about. Well then, what would make something discontinuous? Well, if it's discontinuous, that means that it's not continuous, right? So what would make something discontinuous or not continuous? If this did not hold true, all right? If this did not equal this, or if this did not equal this, then something would be discontinuous. Let's show you in a graph. This one right here, we're going to talk about the most common discontinuities. These are the three breakouts, y'all. We have removable discontinuity. This is the graph we were looking at earlier, and this is when you have a hole, because you've canceled out a factor and you've removed something from this graph. But aside from that, the limit exists. It just doesn't exist at that one specific point, f of c. Okay? Or it could exist. It could maybe it looks like something, before I say it doesn't exist, what if it looked like this? It could be, say you had it evaluated here, right? And this value right here was f of c, right? Because remember, the hole means it does not exist, and a solid circle means it does exist. So when x is c, f of c is the answer. This is the same thing. It's removable discontinuity. The next big type is infinite discontinuity. Well, when something is continuous, there is no breaks or holes in the graph. But when you have a break or hole in the graph, there's a discontinuity. And obviously infinite is when you have a vertical asymptote and you're approaching infinity, whether it's infinity or negative infinity, or both, then you have infinite discontinuity. All right, what's the third big type? We have something called jump discontinuity. And jump discontinuity is just what it sounds like. As you're approaching from one side, you may have a certain value, that's your y value, but as you're approaching from the right side, well, that's approaching some other random y value. So what you have is you have a jump right there, okay? If this one is approaching this value, and this one is approaching this value, you have a jump discontinuity, and the limit does not exist. And so think about it. If the limit does not exist, there's no way that it can be continuous, because right here, if this thing equals this thing, well, if those two things don't equal each other, there's no way that a function can be continuous. Okay. Let's take this idea and look at a few other pictures and see if we understand this. Okay. Let's see. Graph 1. Graph 1. What do you think? I'm going to say, well, as you're approaching, now this is a little a, so I don't care, a, c, 2, 3. It just represents an x value. As you're approaching that a value from this side, and as you're approaching this a value from this side, and quite honestly, if the a just threw you off, call it c. All right, why don't we do that for all of this? No reason to change it to a now, just because I used a different graph. All right, well, the limits don't exist, okay, because you're approaching two different values. That right there is a jump in your graph. That is jump discontinuity. I see myself a vertical asymptote, and as you're approaching c, you are approaching infinities. You have yourself some infinite discontinuity. That's my abbreviation for discontinuity. What do we have on graph 3? Graph 3, well, we have ourselves a little hole, which means we canceled out a factor, and that right there is a removable discontinuity. Graph 4. Graph 4 is still removable just because it's, remember this right here would be f of c, all right? So it is discontinuous, but the limit still exists. The limit equals this value. It's just not continuous. And for this last one here, well, let's see what's happening here. Yeah, that looks like an E, but I just tried to make them all C. I'm just sloppy. All right, well, as x equals C, well, then I guess this right here would be the same thing as f of C, right? Well, that means that the limit as you're approaching from the left equals L, and the limit as you're approaching from the right equals L. And since f of C also equals L, this one right here is continuous. Let us be sure we understand this discontinuity concept by looking at we have a couple more graphs here. So in this graph we have, let's see, let's go from left to right. It looks like we're going from x equals -9 all the way to x equals +9. So in this interval, what types of discontinuities do we have? Continuous. Wait a minute, we have a break. We have a break at x equals -5. What type? Well, that is a jump. It goes from one y value to the next. This is a jump discontinuity. All right, we keep going. So now our graph continues this way, and everything's continuous. Wait a second, we have a hole. A hole, well, something's been removed right there. We have ourselves removable discontinuity. I'm not going to keep writing discontinuity. All right. Yes, it's evaluated here, but all it means is the limit exists, but f of c is a different value. All right, we continue on our graph, and everything is continuous. Wait a second, we're starting to go all the way down towards negative infinity, and then it jumps up here. We're at positive infinity, and we continue. I guess we have ourselves, what does that look like? A vertical asymptote. And vertical asymptotes are infinite discontinuity. I didn't say it, but we have infinite at x equals 5. We have removable at x equals -2. And we have jump, I did say, at x equals -5. If that made sense to you, great. Let's just reconfirm and make sure. Let's look at one more graph, and then we'll be done here. Let's go from x equals -9 to x equals +9. So here is -9 and all the way up to +9. What types of breaks do we have? Well, the graph is continuous. Oh, at x equals -6, we have something. I bet you can tell us what it is. There's a jump right there. That's right. Oh, I meant jump. All right, and then our graph is continuous, going from x equals -9 to 9. But wait a second, at x equals -2, we have a problem. Well, it jumps again. That is another jump. Oh, I can't spell jump. And then we continue on our graph. It's going in this direction, continuous until we hit what x value is that. At x equals -1, we have removable. removable. There we go. And I think we can finish this graph up because for the rest of the interval we're on, it's continuous. That is all continuous. That brings me to a point. Say, for example, I asked you, what is our graph continuous at x equals 3? Well, don't be confused if it's continuous. Just say, yeah, it's continuous. The limit exists from the left and the right, and it equals the same y value.